this limit n goes to infinity, probability that xn equals j. This one is actually a kind of interpretation of stationary distribution, as we discussed before. Okay, and then now we are going to talk about conditional probability. Sometimes this probability depends on the first state, x0. Okay, so now sometimes they are the same, other times they are not the same. Okay, so we are going to talk about this. Okay. Anyway, this one is called limiting distribution of the chain. Limit n goes to infinity, conditional probability, probability that xn equals j, given that x0 equals I. Okay, and if they are the same, I mean this probability, conditional probability does not depends on the initial state. Okay, I mean this one is yes. Then stationary distribution is the same as the limiting distribution. Okay. Before we discuss about existence of limiting distribution, we can think about periodicity. We discussed this last class. So each state has this property, whether aperiodic or not. Okay, state is aperiodic or not, and then periodicity is defined by the greatest common divisor of the steps, such that probability of coming back to the same state with n step, okay, is greater than 0. For such n, we can think about greatest common divisor of the value n. Okay, and then that is defined by periodicity, period of the state I. Okay, and then if the period of state I is equals 1, then we call this an aperiodic state, otherwise periodic state. And then all the states are aperiodic, then we call this chain aperiodic chain. Okay, and as you know, as I mentioned before, if discrete time Markov chain is irreducible, then periodicity of the state can be shared by all the states. As long as one state is aperiodic, then the chain is aperiodic. If the chain is irreducible. Okay. So now I'd like to explain when this limiting distribution exists. Okay. So if the chain is irreducible and positively recurrent, or sometimes discrete time Markov chain is irreducible with finite state, sometimes, right? Anyway, irreducible and positively recurrent DTMC is aperiodic. So all the states are aperiodic. Since this chain is irreducible, as long as one state is one of them is aperiodic, then the chain is aperiodic. Okay. In that case, limiting distribution exists. So otherwise means even though the chain is irreducible and positively recurrent, but the chain is periodic, then there is no such limiting distribution. We cannot find such limit. Okay. But in this case, irreducible and positively recurrent chain, then we can observe a certain phenomenon, like this power of the transition matrix repeat with some step, let's say D. Okay. Okay. After D step, then repeat again and again and again. Then average of the consecutive power of the chain, okay, p to the n power to the p to the n plus d minus 1's power divided by n, divided by d, then this one converges to a certain matrix, okay, a certain matrix. By the way, these three characteristics, irreducibility, positive recurrence, and aperiodicity, okay, as long as a discrete time Markov chain is satisfied with these three conditions, then we can use just one word called ergodic. This chain is ergodic. This chain is ergodic is exactly equivalent to this chain is irreducible, positive recurrent, and aperiodic. Okay. And then, if chain is ergodic, right? As long as the chain is irreducible and positive recurrent, then we can figure out the unique stationary distribution, right? We discussed this before, okay, earlier. And the thing is, the chain is ergodic. That means irreducible, positive recurrent, and aperiodic. Okay. Then, regardless of the first state, okay, this conditional probability, P, probability that x n equals j, given that x0 equals I, and n goes to infinity, this probability converges to the limit n goes to infinity probability that xn equals j. So it is not depending on the first state. Okay. So we can derive in this case, the first case, this limit distribution. This one might be a kind of matrix, right? Square matrix. This square matrix, in the square matrix, in the same column, we can expect all the same values. Okay, and this value might be the same as pi j. Okay, the j is the column index of this matrix. Okay, so then pi j is j's component of stationary distribution. Okay, then in this case, for ergodic chain, j's column of the values in the j's column of the limit limiting distribution is the same as pi j. And even though discrete time Markov chain is irreducible and positive recurrent, if this chain is periodic, okay, then as we discussed before, this value, this limit, okay, converges to the number, and then this number is the same as j's component of the stationary distribution. That's the result. Okay, so for ergodic chain, we can say many things about limiting distribution and stationary distribution. So, is there any question so far? So today we are going to extend the subjects. So now we are going to generalize the case. Okay. Sometimes the chain can contain transient states and positive recurrent states and so on. So as we said before, we are going to consider the discrete time Markov chain. So for now, we are going to consider discrete time Markov chain with finite state, but not irreducible. That is reducible case. Okay. So please think about this example. So what do you think? Is this irreducible or not? Not irreducible, right? We call this reducible chain. Okay, why? If we think about 3 or 4 or 5 states, 3 or 4 or 5, they are transient states, right? So we cannot say that this one is irreducible chain. Okay. So for a general discrete time Markov chain, okay, we can categorize states. We call this canonical decomposition of the states. Okay. Let's say as we used earlier, large S represent the set of states, right? Set of all the states. Okay. And then we can decompose, partition all the states based on these two conditions. Okay. So large T represent set of all the transient state. Okay. So general case, this chain can include transient states, recurrent states, and so on, right? So T represent set of transient state, okay, and C of K represent set of T represent set of transient state, C of K represent set of recurrent state, but for different states, for two states from different C of K, like C of K and C of J. Let's say state 1 is in C of K and state 2 is C of J. They are not communicating. Okay? Okay? They are not communicating. Then we can decompose all the states into in one of T or C of K. K is 1 to some finite number. Okay? So C of K include recurrent states. And inside the C of K, they communicate each other. Okay? But a state in C of K and a state in another, let's say C of J, J and K are different, then they are not communicate. Then we can decompose all the state into T and C of K, K1 to a finite number. Okay? We call this closed set as long as we digit, okay, one of the C of K, state in the one of the state C of K, then we cannot go out. Okay? We cannot exit the we call this subchain. Okay? For example, in this case, okay, in this case, so as long as if we start with state 4, okay, and then move to state 3, and then if we move to state 1, then we cannot exit this chain. We call this subchain. Okay. Similarly, if we entered into the this chain, this lower subchain, then we cannot come back to 3, 4, 5, or we cannot access to 1 or 2. Okay. So we call this subchain. Okay. So for general case, general discrete time Markov chain case, generally this chain includes many states, and then you can decompose, okay, chains like set of state transient state, set of recurrent state, which are communicating each other inside the chain, but cannot exit the chain. Okay. We call this. We can describe this with C of K as a set of states and this set is closed as soon as you enter the one of the state in CK, then you cannot exit the subchain. Okay. So think about this case. Okay. So as I said before, T C sub K represents set, right? So how can you define T in this example? Set of which states? 3, 4, 5. Okay? And then exclude this states. Okay, 3 or 4, 5. We have remaining states are 1, 2, 6, 7. Okay? And then we are wondering whether all the pair of the states among 1, 2, 6, 7 can communicate each other or not. In this case, it's not possible because 1 and 6 we cannot communicate between 1 and 6, right? 2 and 6, 1 and 7, 2 and 7, right? In this case. So they are in different C of K. I mean 1 and 6. Okay? Let's say, think about first C of 1. Okay? So let's start with 1. 1 is communicated with 2. Right? How about 6 or 7? No, it's not possible. Okay? And then we can construct, as we said before, we can construct a smaller chain inside the original chain, right? Okay? So with just 1 and 2, right? 1 and 2. Okay, we call this subchain. How about start with 6? Communicate with 7, but we cannot communicate with other than 7 from 6, right? So we can construct C of 2, C sub 2. And then when we consider union of these sets, C1, C2, and T, then union of T and C1 and C2 is the same as S, right? And no common states among T, C1, and C2. We call this partitioning. We partitioning all the set S into T and C1 and C2 in this case. Okay. Now we are going to talk about how to find limiting distribution of this case. Okay, limiting distribution of this case. Okay, can you do that? Do you know how to do that? So I'd like to introduce this. So easiest one first. Okay, so handling transient states is quite it's not easy to handle transient states to calculate limiting distribution. So let's start with easier one, handling recurrent states, but they are not communicated. Okay. So for all the recurrent states in C sub K, let's say we call this subchain chain with all the states in the same C of K. Okay. And then we assume that this C sub K includes finite number of states, because at the beginning of the slides I explained that we assume the chain has the finite state, right? Okay. So as long as the chain has the finite state, C sub K should have finite number of states, right? And then they are communicate each other. They are a recurrent chain. So we can say that this subchain has the unique station distribution, right? Okay. So for a certain subchain, then we can find the unique station distribution pi sub k. This one is stationary distribution for the k subchain. Okay, k subchain. Okay, and then limiting distribution. When we consider limiting distribution, this p ij to the nth power n goes to infinity, and if I is in C of k and j is in C of k in the same subchain, then this pi j, k represent in the case subchain, right? This one, pi ij to the nth power, is j's component of the stationary distribution of the case subchain. So if we start with one of the subchain, but limiting distribution from the state to the state of the other subchain or transient state, I mean outside the subchain, this limiting distribution might be 0. Okay? Okay? Not easy, right? Okay. So let's think about an example. Quite complicated. We need to introduce new concept F. Actually, this one is very, very difficult to understand, but I'll try to explain as simple as possible. Okay, F. Okay, this F, and first subscript represent one of the transient state, let's say J. Okay, and second subscript represent one of the C sub k, and this one represent limit n goes to infinity, probability that this chain is in C of k given that x0 equals j. If we start with one of the transient states, let's say j, okay, what is the probability that if n goes to infinity, what is the probability that xn is inside the C of k? Okay, that's the definition of f j C sub k. Okay. Okay. Then for j in T, large T, okay, so all the transient states, okay, limit distribution, limit n goes to infinite, P let's say jk, 아니, no, ij, so ij, so I, for I, okay, let's use I, okay, for I inside T, probability that Pij to the nth power, I is one of the transient state, this one is, so we assume that we already know such probability for all transient state and the C sub k. Okay, we assume. I'm going to talk about how to calculate it next class. Okay, but we assume that this value is known. Then this limit probability equals f I C sub k times pi j inside the stationary distribution of the case subchain. Okay, if j is in C sub k, And as I said before, this value is 0 if j is in T. This is the result. But remaining question is how to calculate fi c sub k. Okay. So finding fi sub f sub I c sub k, we need to think about, we need to fix a certain c sub k. And finding so how to find small f I c sub k. Okay, so for a given fixed c sub k, okay, so if first you need to consider one of the c sub k's, okay, and then set a system of linear equation which is f I c sub k equals for all j inside T, one step transition probability from I to j times f j to c sub k. Okay, and then we can think about this for or I inside T. Okay, the number of equation is number of states inside T, right? And what is the known in this case? Small f of j c sub k and small f of I c sub k. Okay. Okay. And one more, all the yes. Okay, you can solve this and then solve this for all c f I c k. This one is fixed. Okay, for all I inside large T.